started. Today in this session, we'll talk about one of the scheduling algorithms called shortest job first. In the previous class, we have seen that there are many scheduling algorithms, and we have seen one of them called first come first serve. But there is one problem with first come first serve. The problem with FCFS is convoy effect. That is, we have divided actually processes into two different categories. One is CPU bound processes and another is IO bound processes. FCFS is not doing fair for IO bound processes. This IO bound processes requires minimum amount of CPU time, and again they will be busy in doing some IO activities, but whereas CPU bound processes takes a lot of CPU time in order to accomplish their task. So FCFS is not fair as far as IO bound processes are concerned. So we have to look for another kind of strategy for achieving task in order to best utilize the resources of a computer. So another algorithm is called shortest job first, SJF algorithm. This is the algorithm actually which is not implemented in any operating system. This is only a hypothetical or theoretical algorithm. Because we have few problems with this algorithm, which we will discuss at end. Let us first discuss how this algorithm works, or what the basic idea behind it. The mode in which this SJF works can be preemptive mode, or it can be non-preemptive mode. Okay. Preemptive means a process can leave the CPU on different events, but whereas in non-preemption, a process can leave the CPU either if it has completed IO, whether it want to do some IO activity, or it has completed its execution. So we'll see first the non-preemption version of SJF. We also call it as SPN, so shortest process next, and the preemption version of SJF we call it as shortest remaining time first. Shortest remaining time first. Okay. Right, and here the criteria on which a scheduling algorithm will select any of the processes among n available processes is the burst time. Okay. The smaller the burst time, the higher priority it will be given for chances of getting the process to be selected for scheduling. Now, when we see this table, process PID, there are 4 number of processes. Okay, process P1, process P2, and process P4, right? And their respective burst times are 6, 8, 7, and 3. When we draw a Gantt chart according to FCFS, then of course process P4 it takes only 3 units of time, but because of other processes P1, P2, P3, the turnaround time for this process goes very high. Okay, if I were asked to draw the Gantt chart for FCFS for this, okay, now there will be no fairness given. There will be no fairness with process P4. Okay, so because the arrival time here, the arrival time is not given, so we assume here arrival time to be 0. When arrival time is 0, so all the processes are present, and I can take any sequence. If we take sequence like this, first process P1 is given chance, then it will run from 0 to 6 units of time. Then process P2, which runs for 6 plus 8, which is equivalent to 14. Then next process P3 will be given, okay, which runs for next 7 units of time. So 14 plus 7, which becomes 21, and the process P4, 21 plus 3, which is equivalent to 24 units of time. Now, when we see actual time which is required for process P4 to complete its execution is 3 units of time, but because of this FCFS, the turnaround time of this process has been increased to 24, which is nearly an order of 7 times has been increased. So it's not fair with this process P4. So in order to not to have this convoy effects, okay, we have an algorithm called SJF. Now let us see, with the help of shortest job first, how do we select processes. Let's draw a Gantt chart. We know that Gantt chart always starts from 0. Now here I have to sort all the processes with respect to their burst times. So, as from the table it is clear that the smallest burst time is for process P4. So, process P4 will be selected for first for scheduling, and this process P4 will run for 3 units of time. Okay. Then next process which takes is 6 unit of time is process P1, which is lesser which is the next shortest job in the available queue. Okay. So, actually I will be having a ready queue here. Okay. In ready queue at time 0, all the processes like process P1, process P2, process P4, process P5 or P3 and P4 all have been submitted to they are present in the ready queue. So, all have been sorted, okay, with respect to their burst times. So, first process P4 is having the smallest burst time, then next process P1, then next process P3 and next process P2. Okay. Now, we have sorted accordingly. So, now when process P4 is completed, because it is non-preemption, it run to its completion. So, process P4 has been completed, the next process P1 will be will be allowed to run. Then process P1 takes 6 units of time, which is equivalent to 3 plus 6, which is equivalent to 9, and then next comes process P3. Process P3 runs for 7 units of time. So, 9 plus 7, which is equivalent to 16 units of time. So, we have completed here process P1, process P3, then the last process is process P2, which runs for 8 units of time. So, 16 plus 8, which is equivalent to 24 units of time. When we compare, of course, the waiting time and the response time for this process for FCFS and SJF, of course, SJF scores. Now, let us talk what is the average waiting time and average turnaround time for each of this for this scheduling algorithm. For that, let us first talk about waiting time for process P1 first. Okay. Now, what is the waiting time for process P1? Now, process P1, P2, all the processes have been submitted to the system at time T0, but process P1 has been given chance at 3 units of time. So, process P1 has waited for 3 units of time. So, waiting time for this process is 3. Okay. And of course, response time is also 3. As I have told, for non-preemption, there will be no difference between waiting time and response time. We see difference between these two timings when we go to preemption. Okay. So, let us not introduce any confusion. So, I am removing here response time and waiting time as same. I am treating here it as same. Next, what is the burst time for this process? So, burst time for this process is, for process P1, burst time is 6. So, turnaround time is nothing but waiting time plus burst time, which is equivalent to 3 plus 6 is 9. Okay. Now, similarly, for process P2, waiting time for process P2 is 16. This is the finishing time, okay, or minus starting time. Starting time is 0. So, waiting time is 16. And what is the turnaround time? Turnaround time is burst time plus waiting time. Okay. So, burst time for process P2 is 8 plus waiting time is 16. So, it goes to turnaround time for this process is the waiting time is 16, of course, okay, plus burst time is 8, yes. So, it is 24 units. Then for process P3, here we will do for process P3. Waiting time for process P3 is, it has been submitted to the system at time 0, but has been given chance after 9 units of time. Here arrival time is 0, we assume arrival time to be 0, and the turnaround time is equal to waiting time plus burst time, which is equivalent to 9 plus burst time of process P3 is obvious from table, which is 7, 16 units of time. Then for process P4, What is the waiting time for process P4? The waiting time for process P4 is 0, because it has been submitted to the system at 0 time, and it has been scheduled at the same time when it has been submitted. So waiting time is 0. So in the best case, the turnaround time will be equivalent to the burst time or service time. It is also called as execution time. So 0 plus P4 has 3 is equivalent to 3. Now let's find out average waiting time for this process in SJF non-preemption, SPN. Waiting time is for process P1 it is 3 plus process P2 it is 16, for process P3 it is 9 plus process P4 it is 3. So by total number of processes are 4. This is average waiting time. So 9, 10, 11, 12, 13, 14, 15, 31 by 4. So 28, 29, 30, 31, 3, 4, 8 are 32, so 4, 7, 28. So 7.7 units is average waiting time, and average turnaround time is the sum of turnaround times is 9 for process P1 and 24 for process P2. I am sorry, average waiting time for process P1 is 3, for process P2 is 16, and process P3 is 9, and for process P4 it is 0. Okay. So it is 0. So it changes. 25, 26, 27, 28. 28 by 4, 7s are 28. Okay, 7 units. And average turnaround time is 9 plus 24 plus 16 plus 3, yeah, by 4. So it gives you how much is 20, 23, 33, 34, 35, 36. 36 plus 16, 52. It's simple addition. 24, 16 is 19 plus 9. So 19 plus 9 it gives 23. 9, 10, 11, 12, 42. Okay, it's 42 by 4. So 4 ones are 4, 10s are 0 point 4 something, these units of time. These are turnaround time for this SJF. Okay, the problem here is the problem here is, how do we know that we cannot predict future? How do we know that this process P4 will take 3 units of time, process P1 will take 6 units of time, process P3 takes 7 units of time? We don't know actually. So that's why this theoretical. Okay, practically, if we want to know how do we know the burst times for this process? There are 2 ways in which the burst time for the process can be calculated. Okay, one way is in batch system, user will specify there are 2 ways in which this burst time can be given. One is in batch systems, generally user will specify. Okay, it's common scenario. But whereas in interactive systems, we don't know. So here we have to estimate. We have to estimate the burst times. So estimation of the burst time can be done with the help of exponential average technique. Estimating the burst time with the help of exponential averaging technique. Okay. Now, how do we do that? We'll solve one problem on this as well, right? But before we do this, we'll first complete this preemption mode of SGF, which is called as shortest remaining time first. Now, let's talk about preemption mode of SGF. Now, in preemption, how this algorithm works? The basic idea is, when a new process is added into a ready queue, assume that we have a ready queue and here we have few processes. When a new process enter into the ready queue, process Pi, okay, then a scheduling decision will be taken, including the current process which is running in the CPU. Suppose there is CPU and there is one process called Px which is running on this CPU, and when a new process is added into a ready queue, then what this algorithm will do is, this algorithm will again sort all these processes with their shortest remaining time and how much time they need for to complete their execution, including the current process which is running, possibly preempting it. Meaning, if this process PA is incoming process, okay, it has less time for it has very less time to complete its execution, but this process Px has time, but it takes more time than this Pi, then this process Px will be preempted and Pi will be given chance on CPU to execute. Okay. This is called shortest remaining time first. So here we'll write the basic idea. The basic idea is, whenever a process is added to a ready queue, processes are sorted with respect to shortest remaining time, including the current running process, possibly preempting it. The difference between this and this is, suppose this process takes only 3 units of time and this process takes 2 units of time. The remaining time for process Px is 3 units of time and the remaining time for process Pi is 2 units of time. Then in preemption mode, process Px will be taken away from CPU and Pi will be given this CPU. But in non-preemption mode, okay, it will complete its execution, then after this process Pi will be given chance. Okay. This is the difference between them. So here scheduling decision is taken whenever a process is added to a ready queue. So keeping this in mind, let us find out what is the average waiting time and average turnaround time for this process. Okay. So we'll take the same example. If we take the same example here, if we take the same example, then I think we don't give any difference. Okay. Here, if you take the same example, then preemption and non-preemption works in same way. So what do we do is, we'll take another example in which arrival times have been given, and then we'll try to solve this with SJF, with SPN and SRT, and compare how they work. Okay. For that, we'll do small modification to these programs, right? So I'll do these modifications as follows. So we'll add arrival time here. arrival time for these processes. Okay, and let's give bus time to be 8, 4, 9, 5, and arrival time is 0, 1, 2, 3. Okay, this is the arrival time. Now, keeping this, now let us find out average waiting time and average turnaround time with these two algorithms and see how the behavior changes with preemption and non-preemption. Okay, I am first solving this problem with non-preemption first. Okay, so I'm doing SPN, shortest process next first. Okay, now let's draw a Gantt chart. You know that Gantt chart starts from 0. Okay, now at time 0 I have a ready queue. At time 0, please take down this table, so it will help you in writing this Gantt chart. Okay, so now at time 0, process P1 enters into the ready queue. So when process P1 is entered, then process P1 will be given chance for its execution, and it will execute to its bus time. So the bus time is 8 units of time. So after 8 units of time, it means 8 from time t is equal to 0. Now we are at time 8. At time 8, at every time, like at time 1, process P2 has been added, and at time 2, process P3 has been added, and at time 3, process P4 has been added. So all these processes have been added. Now here I have to select in non-preemption, I have to select the shortest job or shortest bus time among the remaining, which is P2, P3 and P4. So I cannot avoid P1 because at time 0 P1 was available. I have no other process to schedule. That's why we have given chance for process P1. But once process P1 is given to CPU, it will not be preempted because it's working in non-preemption mode. Okay. So now then if we see the bus times, then process P2 of course has less bus time. Process P2 is of 4, so 8 plus 4 is equivalent to 12 units of time, and process P4 next, which is having 5 units of bus time. So and then next process P3 will be given chance, and it has bus time of 9. So 17 plus 9 is equivalent to 26. Okay. Now here we will record the turnaround time and average waiting time and average turnaround time of each of this process. Okay. First, the waiting time for this process P1 is 0, and waiting time for process P2. Okay. Now here the waiting time for process P2 is of very importance, because the arrival time, the process P2 has arrived at time 1, but it has been given chance at time 8. So 8 minus 1 is the waiting time for process P1, meaning at time 1 process P2 has been submitted to the ready queue, but because process P1 is running, it has not given chance. So at time 8 process P2 has been given chance, meaning in this time interval, which is 8 to 1, 1 to 8, which is equivalent to 8 minus 1, 7 units of time process P2 has waited. So now here, because the arrival times have been given, calculating waiting time is of importance. So we should not write here 8, we should write here 8 minus 1, which is starting time or the response time, or we can write here as waiting time can be calculated as response time minus arrival time, okay, or starting time minus arrival time. So now next is process P3. Process P3 has been submitted to the system at 2 units of time, but it has been given chance as 17. So 17 minus 2 is the waiting time for this process. Now process P4 was submitted at time 3, but was given chance at 12. So 12 minus 3 is the waiting time for this process. Okay. Now this is the average waiting time. To simplify, 1, 2, 3, 4 processes. Okay. So is equivalent to 0 plus 7 plus 15 plus 9 by 4, 24 plus 7, 24 plus 6, 31 by 4. So which is equivalent to 4 7s are 28, 3. So 4 7s are 28, 29, 30, 31, 3, 0.047 are. So 7.7 units, we get something around this. Okay. So average turnaround time. So turnaround time is nothing but waiting time plus burst time. So waiting time for process P2 is 0 plus burst time is how much? For process P1 burst time is 8 plus waiting time is 7 for process P2 and burst time is 4 plus waiting time is 15 plus process P3 burst time is 9 plus 9 plus 5 which is for process P4, then again divided by 4, this will give us average turnaround time. So simplify, 8 plus 11 plus 24 plus 14 by 4, so it gives 19 plus 8, 38 by 4, so 9, 16, 17, 7, 4, 5, 57 by 4. So which is equivalent to 4 1s are 4, 4 4s are 16, 0.4 to the 8, so 4.2 units. Okay. So now here we will note down. So average waiting time for SPN, shortest process next, is 7.7 units, and average turnaround time for this is 14.2. Okay. Now the same problem we will solve with the help of shortest remaining time first, and we will see the results. Okay. How does it goes on? So how do we change the average waiting time? See, the main focus of scheduling algorithm is there are many times associated with a process. A process has waiting time, a process has turnaround time, a process has burst time, a process has response time. Always I tends to reduce response time, reduce waiting time, reduce turnaround time. No, burst time neither can be reduced nor it can be increased. So it is constant. There is actual time which is needed by the process, right? We cannot do anything with the burst time. So more I decrease these times, response time, waiting time or turnaround time, then better the algorithm is. So now let us draw for shortest remaining time first. We know that it works in preemption mode. So this is the Gantt chart. Okay. Now here ready queue plays a very important role. Actually in every algorithm it plays, but here because of preemption and remaining time and the criteria on which the decision will be taken, depending on that we have to be very careful that which process will be given chance. So for that I have to write it here: process P1, okay, process P2, process P3 and process P4. The burst time is 8, burst time is 4, burst time is 9 and burst time is 5, okay, and the arrival time is 0, 1, 2, 3 for example. So this is the table we have, right? Now what happens at time 0? Nobody is there, so process P1 is submitted to the system. When process P1 is submitted to the system at time 0, it will execute for 1 unit of time. At time 1, at time 0 process P1 is given, but at time 1 another process called process P2 is entered into the ready queue. Okay. When it is entered into the ready queue, now this algorithm takes decision. So how much remaining time for this process P1? process P1 has already executed 1 unit of time, right. So, which is equivalent to 8 minus 1 is 7 unit of time is remaining, and for process P2 only 4 unit of time remaining. Okay. So, which is shortest remaining time? Shortest remaining time is for process P2. So, preemption happens. Preemption happens. When preemption happens, what happens? Process P2 will be given chance. Process P2 will be given chance. Okay. When process P2 is given chance, now it will execute for again one more unit of time at time 2. So, at time 2 again another process is coming, which is process P3 is submitted to a system. When process P3 is submitted to a system, okay, now let us find out what is the remaining time here. Okay. Remaining time for process P3 is 9 and remaining time for process P2 is only 4 minus 1, which is equivalent to 3, and remaining time, now it will find out the remaining time for all the processes which are there in ready queue. Okay. The remaining time for process P1 is 7 here, and process P2 is 3 and process P3 is 9. So, shortest remaining time is again P2. So, P2 is again given chance. So, it will run for one more unit of time. So, at time 3, at arrival time 3, another process P4 comes. When another process P4 comes, now again it will find out the remaining time. So, remaining time for process P1 remains same, but process P2 it has executed for 2 units of time. Okay. So, process P2 has been executed for 2 units of time. So, remaining time for process P2 is only 2. Earlier it was 3, but now it is 2. And for process P3 it is 9, and for process P4 it is 5. Okay. So, again shortest remaining time is for process P2 only. So, next at 3 and 4 also. So, process P2 will be given chance for up to 5. Next unit, 2 units of time will be again given to process P2. So, process P2 has completed its execution. Okay. Process P2 has completed its execution. Now, when process P2 has completed its execution, now what is the shortest remaining time? Now, P1 will not be given chance. For P1 remaining time is 7, but for P4 remaining time is 4 only. So, process P4 will be given chance. Suppose while making this decision, suppose one more process enters into, then again this algorithm work by calculating the remaining time and scheduling an appropriate process. So, process P4 will be given chance, which runs for remaining 5 units of time, which is equivalent to 10 units of time. Okay. So, process P2 is also completed. Okay. Then the remaining time, shortest remaining time will be for process P1. So, process P1 will run up to 7 units of time, which is 10 plus 7, which is equivalent to 17. Then it gets completed. Okay. Then next comes last, process P3 will be given chance. Okay. So, it will run up to 9 units of time, which is equivalent to 26 units. Okay. See, ending time will be same for all this. Okay. But now let us find out how the average waiting time and turnaround time reduces for this algorithms. Okay. I think here the concept of ready queue is important here. Ready queue is implemented, how it is implemented here, okay, and how the selection of the process will be made from a ready queue is very important. Now, let us find out waiting time for process P1. For process P1, what is waiting time for process P1? Now, starting time for process P time is 0 minus arrival time for process P1 is 0, which is equivalent to 0. So, process P1 waited 0 amount of time, and turnaround time is of course waiting time plus burst time is equivalent to no. So, now here turnaround time is of difference. Now, here it changes because we have a concept of response time here and also turnaround time here. Now, waiting time, now let us find out what is the waiting time for process P1. In non-preemption we were doing this, but in preemption waiting time is not 0 for process P1. Response time for response time is nothing but it is the time interval between a user has submitted the input and it has started getting the response. It is not necessarily that getting the output or got the output, it is started getting the output or started getting the response. This is called response time. So when a process P1 has been submitted, it has started giving response. So response time is 0, but waiting time is here first response time is 0 minus arrival time is 0 plus. Now again we see in Gantt chart P1 is available anywhere. Yes, P1 is here. It means out of this 8 units of time, only 1 unit of time has been executed, and 7 unit, in order to execute remaining 7 units, the process P1 it has been made to wait up to this interval of time, from 10 to 1. It means it has to wait in this duration of time. So how can I get this interval? 10 minus 1 will give me this interval, right? This interval. 10 minus 1. So 10 minus 1. So this is what process waiting time. So again we don't have, so this is the total waiting time. This is also called as total waiting time. In non-preemption, there is no difference between waiting time and response time. Both are same, right? And it's very easy to calculate turnaround time because waiting time plus response time is turnaround. But whereas in preemption algorithms, response time is different, waiting time is different, and calculating turnaround time, in order to calculate turnaround time, we should calculate total waiting time of a process, which is actually this total waiting time. So which is equivalent to 9. So now turnaround time will be what? Total waiting time plus burst time is equivalent to 9 plus 8, which is equivalent to 17. So turnaround time for process P1 is 17, but earlier case it was 8. Only this process, because of non-preemption, it has been given the chance. This is good for process P1, but this decision is bad for process P1. But the bad decision for P1 has been proved good for remaining processes. But here it has not proved good for remaining processes. We will see now. Then next we have process P2. Process P2, response time for process P2 is, now starting time is 2 minus arrival time of, starting time for process P2 is 1 minus arrival time is 0. Now here we see the response time for two processes has been made it to 0, 0, but whereas never we will get here, two processes are having response time of 0 if they are submitted at the same time. But here, because of this difference in arrival times and their remaining times, they have got response time to be 0. So let's find out total waiting time for this process. Process P1 waited for 1 minus arrival time, which is 1 minus arrival time, which is 0 plus so 0. So total waiting time for this process P2 is also 0. That's good. And turnaround time is, waiting time is 0 plus burst time. So this is the best case. This is the best decision for process P2. Now when we look here, is it not favoring IO bound processes? SJF in preemption called shorter remaining time is favoring more to IO bound processes. So it's good, thereby avoiding convoy effect and better utilization of computer resources. So turnaround time for process P2 is only 4. So 4 units of time. Now let's calculate for process P3. Response time for process P3 is 17 minus when it has been submitted at time 2. So 15 is the response time. And total waiting time, here total waiting time is, here in this case, specific case it is same, but it may change, like how for P1 it has been changed, because we don't have any other process with shortest remaining time, we have got it same. but generally we cannot guarantee that always they can be same, they may be different. So, it is 15 again. So, turnaround time is 15 plus burst time of process P3 is 9, which is equal to 24. Okay. Then process P4, we will write process P4 here. Okay. Response time for process P4 is 5 minus, when it has been submitted, is 3. So, response time is only 2, and what is total waiting time for this process? Process P4, same, 5 minus 3 is equivalent to 2. Again, it is not existing in Gantt chart, that is why we do not take it. So, turnaround time is 2 plus burst time for process P4 is only 5, which is equivalent to 7. Okay. So, with these values, now let us find out what is average waiting time and average turnaround time for this process. What is the response time as well. So, here we have to calculate in preemption 3 things: average response time. Okay. So, what is average response time for process P0? Response time is 0. For process P2, the response time is again 0. Then for process P3, the response time is 15, and process P4, the response time was only 2. So, by 4, so it gives 17 by 4. Okay. Now, average waiting time. So, what is the waiting time for this process P1? Process P1 waiting time is 9, 0, 9 plus 0 plus 15 plus 2 by 4. So, 24, 25, 26 by 4. I think this is far lesser than this. Okay. 4 6 are 24, 4 7 are 28. Yeah. So, average here you are getting 7.7, but here what do you get? 1 3 by 2, 13 by 2 is 6.6, 2 6 are 12.5, 6.5. So, when we compare, the average waiting time here is 7.7, and here we have got 6.5. So, it has been reduced. Okay. And let us find out average turnaround time for this. So, average turnaround time for process P1, it is 17. For process P2, it is 4 only. For process P3, it is 24. Process P4, it is 7 only. So, 24, 28, 29, 35 plus 17, 4, 2, 10, 12, sorry, 12, 3, 4, 5, 52 by 4. So, if you do 52 by 4, so we will get 4, 13. Yeah, we have got 13, and here we have got 14.2. Here also we have reduced, turnaround time also. Okay. So, this is how preemption work, but here we have overhead of context switching. It takes some little amount of time for switching from one process to another process, because all the registers have to be copied into the the context of the CPU has to be copied, and it has to be reloaded with the new process, and the new process has to be allowed to execute. So, little overhead, however it will be, but you are gaining gaining in throughput by reducing the response time and waiting time and average turnaround time of this process. Okay. Now, let us discuss the problem with SJF. This SJF is the scheduling algorithm which is not implemented in any operating system. Why? Because this is not real, because nobody can predict the burst times for the processes. Then the question arises, why this algorithm is? Now, yes, we cannot find out the burst times for a process, but we can estimate, we can just predict the burst times by seeing current information. With the help of current information and the past history, we can predict what will be the next CPU burst. Okay. Now, it can be done with the help of exponential averaging system. Okay. And according to the exponential averaging technique, it has been given that tau of n plus 1, this is the next CPU burst. Okay. Predicting or estimating. So, how do you estimate the next CPU burst? The next CPU burst can be estimated with the help of a constant called alpha. It is calculated. How it is calculated? Then and this value is constant value which has to be multiplied by T of n. This T of n is nothing but is most recent information available. Most recent information plus 1 minus. Now, remember, the alpha value cannot be, it should lie between this value 0 and 1, 0 and 1. It cannot exceed those. It cannot be negative or it cannot be more than 1. Then this tau of n, which is past history. Now, this is called exponential averaging technique. With the help of this, we can estimate the next CPU burst. Now, what happens if the value of alpha is 0? Okay. Case A, if alpha is 0, then tau of n plus 1 becomes tau of n. Okay. What case B? What happens if alpha is 1? It means I am taking the boundary conditions. If alpha is 0, what happens? Tau of n plus 1 becomes tau of n, and alpha is equal to 1, then what happens? When it becomes 1, then tau of n, this value will become 0, then tau of n plus 1 will become T of n. Okay. So, with the help of this, we can estimate the next CPU burst. Now, it would be this can be understood better if we will do one problem on this. So, we will take one problem that suppose if a system is having n process, I will just write the question. This is the question. 1 minute. So, we will do one problem on this. Okay. Given a system using SJF, using SJF and exponential averaging with alpha is equal to 0.5, what would be the next CPU burst for a process with burst times of 5, 8, 3 and 5. Initial value, this past history is given, tau of 1 is equal to 10. So, how do we find this value? Okay. So, given a system using SJF and exponential averaging with alpha is equal to 0.5, what would be the next CPU burst for a process with burst times of? So, now this is the most recent history which is available, called 5, 8, 3 and 5. Okay. So, they are in total of 4. So, it is asking us to find out the next CPU burst, which is 5th. So, my tau of n plus 1 is equivalent to actually tau of 4 plus 1 is equal to tau of 5. I have to find out tau of 5, but what is given? This is what I have to find out, but given is tau of 1 which is equivalent to 10. Okay. Now, this is recent information which is given with okay. So, this is the recent information is given for Tn values, okay, T1, T2, T3. Now, what do we do is, let us find out, how do you find out tau of 5? Tau of 5, now we have formula, recall the formula is tau of n plus 1 is equal to alpha of T of n plus 1 minus alpha of tau of n. Okay. Now, if I want to find out tau of 5, then I have to find out alpha of 5 can be written as 4 plus 1. Okay. So, T of 4 plus 1 minus alpha of T of 4. Okay. But I do not know T of 4 again. So, how do we calculate tau of 3 plus 1 is equivalent to 4? So, this can be calculated again using alpha of tau of 3 plus 1 minus alpha of tau of 3. Again, we do not know tau of 3. So, tau of 2 plus 1 is equal to alpha of tau of 2 plus 1 minus alpha of tau of 2. Again, I do not know tau of 2. So, what do we do is tau of 1 plus 1 is equal to alpha of tau of 1 plus 1 minus alpha of tau of 1. So, it is good that we know this tau of 1. So, let us do let us find out tau of 2. This is actually tau of 2. Okay. So, alpha value how much? It is 0.5 into tau of 1. So, this is T1, T2, T3 and T4 given. So, T1 is 5 plus 1 minus 0.5 is 0.5, 1 minus alpha value is also 0.5 of T of 1. T of 1 is given is 10. So, the value becomes 2.5 plus 5 is equivalent to 7.5. So, tau of 2 becomes 7.5. Now, this 7.5 I have to substitute here. It's some kind of recurrence relation kind of stuff. Okay. 0.5 again, then T of 2 is 8 plus 0.5 into tau of 2 is, we know that 7.5. Okay. So, we will do good mathematics for this. Okay. 5 8s are 40, 4.0. Okay. Now, yeah, plus 7.5, 75 into 5, 25, 35, 36, 37, 3.75. So, 4, 5, 6, 7, 7.75 we got. This is the value of tau of 3 actually. Okay. So, 0.5 into tau of 3 is how much? 7.75 plus 0.5 into tau of 3 is equivalent to 7.75. Oh, great. So, 7.75 into 0.5. So, 25, 35, 36, 37, 35, 36, and 38. So, after 3.875 plus 7.75 into again 0.5. 25, 35, 36, 37, 75, 35, 37, 38, okay, 3.75, no props, 2, it is reducing here, how come? Sorry, yeah, that is what, it should not reduce. So, I did mistake, so here it should be 3, yeah, so, sorry. So, yeah, so we got this value 3.875, this is actually T3 is 3. So, 5 3 is 15 is equivalent to 1.5, okay. So, 1.5 plus 7.75 into 5, okay. Let us find out what is its value, 25, 75, 35, 36, 37, 7 5 the 35, 36, 38, 38, so 3.875, okay. So, the value will be this is 1.5, so 5, 7, 8, 9, 10, 13, 3, 4, 5.735, so 5.735, okay. Because of this 3 it has been reduced, right. So, it means we cannot take any hard and fast rule that the value should always increase, it may decrease because it may depends on the information what do we have. So, alpha value will be 0.5, now T4 is 5 plus 1 minus alpha 0.5 is tau 4 which is equivalent to 5.735. So, 25 2.5 plus, okay. So, let us do this multiplication, 5.735 into 5. So, 25, 15, 16, 17, 7 5 are 35, 36, 25, 28, 3, 4, 1, 2, 3, 4. So, 2.8675 plus 2.5. So, 5, 7, 6, 8, 9, 10, 13, 5.3675. So, now we have estimated the next CPU burst depending with the help of this exponential averaging technique. So, tau of 5 would be, this is an estimated value 5.3675 units. So, the problem with SJF is we cannot find what is the next CPU burst. We cannot tell 100% this will be the next CPU burst, but we can estimate. This is how the estimation can be done with the help of exponential averaging system. Okay. So, but there are few problems with actually this cannot be implemented. This can be implemented with the help of this technique. Otherwise, we do not know that what is the next CPU burst actually. So, let us go to next algorithm called priority scheduling algorithm.